So this session was originally intended to be challenges to inflation. And so in that spirit, I would actually like to start with the challenge for inflation. So let me just write that down. But this is only meant to whet your appetite. The bulk of the talk will be on topological defects. But I thought it would be a shame not to mention the challenge. So as Matthias pointed out in his lecture, if you look at the CMB in opposite directions, you see the same temperature. So that's called the horizon problem. So basically, the problem is that you have some region, there are photons coming from either side, and they are at the same temperature, T left and T right, and they are equal. And of course, these regions have been out of causal contact, and so this seems like a mystery. And what inflation does is that it goes back, and now you have a small region over here. And this big region is supposed to come from this little region, and the small region is supposed to be in causal contact. And if it's in causal contact, it can smooth out. So causal and it's smooth. And if it's smooth, then it sort of becomes easier to understand that the smooth patch just became larger, and that's why you see the isotropy. But you can actually look at this a little closer, and you can show that this smooth patch itself has to be superhorizon. So the point is that it's a smooth patch compared to this patch, but it's not a small patch compared to the horizon at this epoch. So you might say, how do we see this? So the proof is not too hard. And instead of going through equations, I will just show it to you in pictures. Imagine a space-time diagram, time, space. And let's say you're in an FRW, and there's this horizon. And now you want to take a small patch, a sub-horizon patch. Let's say you take this patch, and you want it to start inflating and become huge, so that you can understand what the smoothness in that region, similar to this. So if there is an inflating region, so let's say there's inflation over here. Right, so you have a small region. Say even we can take today's FRW, take a small region and try and blow it up using inflation. But then you can imagine that there are light rays that start outside and go inside. Okay? And in gravity, there's something called the divergence of these rays, and so theta is the divergence. So there's Ray-Choudhury's equation, which is this is equal to various things, but from here you can show that d theta by d tau has to be less than or equal to minus r and n. Okay, where n are the null vectors. Basically, all this is saying is that if you start with diverging rays, then gravity tends to make them converge, right? Gravity is always attractive, so it's making things converge. Outside the horizon, right? Even if you send rays in, they're actually moving out, and so they're diverging. Okay? So outside the horizon, if you send rays out, of course they're diverging. If you send rays in, they are still moving out, so they're diverging. However, this point A is inside the horizon, so this is converging, right? Because I'm sending rays in. But here, this is outside the horizon, the inflationary horizon, so this is diverging. So just this kind of space-time diagram implies that this quantity should become negative, but this, by Einstein's equations, is just minus T mu nu, N mu, N nu. So it means that which in terms of fluids would be something like rho plus P. So that would mean that you must have rho plus P become negative. So if you want a causally connected region to become a horizon, then you must have violations of the null energy condition. Okay? So in that sense, all that you can do is to change the diagram and start with a patch that is larger than the horizon size. And then, of course, there is no contradiction. Okay? So inflation, even to begin, must begin with a superhorizon patch, which then becomes much larger. And of course, there's an advantage to that, which is that here you might start with maybe 10 horizon sizes, but here it becomes much larger, 10 to the 88 or whatever. So there's an advantage, but you really, in my mind, you haven't really solved the horizon problem. You've just mitigated it. Okay. Okay. There's another way you can think about the same space-time diagram, and these are called embedded diagrams. And so basically what you're saying is that you start with some spatial slice, and let's say the horizon is this big, but now you want to create inflation in a small region. So you start inflating here, and then eventually it becomes like this, and the horizon is this big. But you see, you have this neck over here. To keep the neck open, you have to fill it in with rho plus P negative. You have to violate the null energy condition. So that's another sort of pictorial way of seeing that you need violations of NEC to really solve the horizon problem. Of course, if the initial patch is larger than horizon, there is no such problem because now the neck is kept open by the background expansion. If it's super horizon, the background expansion keeps this neck open. All right. So you can find a written discussion of this in GRQC. Sorry. Okay. So let's see. These violations of NEC come up in many places, and they also come up in eternal inflation. So in eternal inflation, you have some potential. This is your phi, this is your v of phi, and the field is rolling down, but periodically it jumps up, and it jumps up by quantum effects, suppose. But these, and what happens is that inflation is slowing down over here, but all of a sudden you get this quantum kick, and then there's a little pocket where you get even faster inflation. And in this way, inflation never ends, and it's called eternal inflation. But this jump, you can show, violates the NEC. And then, of course, there's this effect. Then you can ask, do quantum field theory effects violate NEC? And you can show that they do. But what you don't know is that if a quantum field theory effect violates NEC, what's the effect on the background metric? So anyways, so basically my challenge for inflation is to start it from a sub-horizon region to really solve the horizon problem. Of course, you can always say that it's a probabilistic thing, that maybe by chance there was some region which had the right conditions for inflation, and then inflation took over. And I think that's a fair way to look at it. In fact, I think that any cosmological model will have to be based on quantum or statistical principles, and so you will always be talking about probabilities, and so there's always a probability that inflation will start somewhere. There's always a probability that FRW will come up somewhere. So okay, that's all that I want to say about the challenges for inflation. I'm sure Neil would have many more challenges, but this is one of my challenges. Okay, any questions about this? Yeah, so violating the null energy condition is effectively you make wormholes, and with wormholes you can have closed time-like curves, and so you get into all those problems.
So if you started inflation by violating it, I mean, would you expect to observe such objects now or anything like that?
That's a good question. I don't know the answer to that. I mean, it may not be so bad, because in quantum field theory, you know that the NEC is violated. But the question is to violate it in a sense, in a way that makes that sort of then freezes and becomes your universe. That's the reason for it. So it's, and again, when you talk about quantum field theory, you're talking about probabilities, right? And so with a certain probability, this can happen. But is that really a solution to the horizon problem? Okay. So yeah. All right, let me move on to topological defects. And I am going to base this on a recent review well, at least some of it. So if you want to follow up, that's a good place to start, because it has references to earlier work. So here I want to start by saying that that early universe cosmology is all about remnants. Okay, so. And basically, remnants are objects that were created in the early universe that didn't thermalize. I mean, if it gets thermalized, then it's washed out. So you have lots of examples. There's dark matter. There can be magnetic fields. And then there are magnetic monopoles. Cosmic strings. And there can be many other things, but these are some of the popular remnants. And the exciting thing is that you can put constraints on all of them. And since these remnants are supposed to come from some particle physics phenomenon, you can probe particle physics at the very high energies by looking at these. So, for example, a probe of string theory would be to look for these remnants. So, so the constraints might be, for example, for magnetic fields, there's a BBN constraint, which is a Big Bang nucleosynthesis constraint, which is that omega in B is less than 10 to the minus 5. For magnetic monopoles, if you take one magnetic monopole per horizon at formation, then if you take one monopole per horizon at formation and you calculate the density today, and you require that the density be less than critical today, then this gives you the mass of the monopole has to be less than about 10 to the 11 GeV. And as you probably know, that this is the reason for inflation, that grand unification was supposed to happen at 10 to the 16 or 10 to the 15 GeV. The magnetic monopoles from grand unification would be 10 to the 15, 10 to the 16 GeV in mass, and they would overclose the universe, even if you assume there was only one monopole per horizon at formation. So this is a nice constraint. And of course, there's another constraint called the Parker bound. The Parker bound is a constraint of how many monopoles there can be in our galaxy. Basically, the idea is that if you have magnetic monopoles in our galaxy, then they get accelerated by the galactic magnetic field. And so the galactic magnetic field is doing work on the magnetic monopoles, and the galactic magnetic field should decay. But we see a galactic magnetic field, so that limits the number of monopoles in our galaxy. I'm not going to quote the number because it's not on a mass, but on the density of monopoles. And another, so these are, of course, topological defects. And I will discuss cosmic strings in some detail now. Okay, so maybe I'll. So let me discuss cosmic strings. So in field theory, you discuss the vacuum of the field theory, but in cases even like in the electroweak case, we know that there is not one vacuum, but there's a whole vacuum manifold. So there's a vacuum manifold. And the vacuum manifold can take funny shapes. So it can be a circle, it can be a sphere, it can be a torus, it can be all sorts of things. For example, if you have a complex scalar field and you require that its modulus be 1, this is the minimum of the potential, then of course this is a circle, right? Because it's basically phi 1 squared plus phi 2 squared is 1. So the vacuum manifold sort of becomes relevant at a phase transition. So when you have a symmetry breaking, all of a sudden the field has to decide to live on one point or on some point of the vacuum manifold. So for example, let's see, now I have to do this juggling. So you can imagine some region of space, and the field has to decide on which point of the circle, on which vacuum should I go. So you have regions, domains of certain different vacua. So for example, the angle on the circle can be 0 here, can be pi by 2, etc. Okay, so the system has to decide locally that I am going to go into this vacuum. Over here, I'm going to go into this vacuum, right? And the two are not talking to each other beyond a certain distance, and that is why you get funny effects, and which we will discuss. The kind of vacuum we're interested in, so let's call this vacuum manifold to be sigma sub vacuum. So what we want is that phi 1 of the vacuum manifold be non-trivial. Now pi 1 is the first homotopy, the first homotopy group. It's basically just to understand is that there should be paths on the vacuum manifold that cannot be shrunk to a point. Okay. All right. So the vacuum manifold should have holes such that a one-dimensional path on the vacuum manifold cannot be shrunk. So for example, if you have the circle, then you can wrap around the circle n number of times, and without cutting that path, you cannot shrink that path. Okay. So why is this? Why does this give rise to interesting effects? It's because if you imagine in the xy plane, you take a circle, and let's say this is a circle which is phi 1 plus I phi 2, right? Then on this point of the circle, I can map it to some point here. This point I can map here, and so on. It can happen that as I go around the circle in space, I go around the circle on the vacuum manifold. Okay? But what does that mean? It means that as I keep shrinking this circle, I will be forced to leave the vacuum manifold. Okay? Because if I didn't leave the vacuum manifold, there would be some point over here at which the field would be ill-defined. It would have to wrap at one point. Okay? So the field would be ill-defined at that one point. So the only way out is if there is a point over here where phi is not in the vacuum manifold. Okay? But if it's not in the vacuum manifold, there's energy over there. Okay? Because by definition, the vacuum manifold is where the energy is 0, but now you're forced to get off the vacuum manifold, and so it means that there's energy over there. And now, if you lift this path in the perpendicular to the board, then you have a whole string of points where the energy is forced to be non-zero. Okay? And this locus of points where the energy is non-zero is called a string. Okay? So just from the fact that your vacuum manifold has incontractable paths, you are forced into the existence of these string-like objects. Okay. But this is the simplest situation. You can have other complicated situations, and let me describe those. So this was when the vacuum manifold was a circle. But you can have a vacuum manifold which is something like, say, a two-sphere with opposite points identified. Okay? So in fact, this happens in a pneumatic liquid crystal also, that you have the vacuum manifold for these liquid crystal molecules are such that they like to lie on a sphere, but it doesn't matter whether they're pointing this way or this way, because they don't point. They're kind of symmetric. So that's the Z2. And now in this case, what it means is that the north pole, for example, is identified with the south pole. So you have a path that goes from the north to the south, and that's a closed path because the north and the south are identified. And so this has incontractable paths, and you get strings. But you see, if you put two of those strings together, if you go from north to north, then this is not incontractable because you can shrink it off, which means that the string, if you put two strings together, then that is equal to nothing in this sense. Okay? Because there's a actually there's a nice trick you can do with the belt that illustrates this, because it's the same topology in the rotation group. And might as well show it. Huh? I'll have to take off my belt just for a minute. You probably, some of you might have seen this. You take a belt, right? The idea is that this is a closed, so this vector has to be the same as this vector, okay? But now let's say I put a twist in the belt by 2 pi, right? And now it's closed, so I can't move this vector relative to this vector. So the question is, can I undo this twist by keeping the ends always parallel, okay? That's the rule of the game, the closed path, okay? So I might be able to do this. I'm always keeping it parallel. But you see, I can't undo the twist. Okay? Convinced? But now let me do a 4 pi rotation. So twist it 4 pi, right? And now if I do the same operation, I get nothing. So this is a property of the rotation group. And in fact, that's what comes in over here. In pneumatic liquid crystals also, it's the rotation group. And so if you rotate by 2 pi, then you're stuck. But if you rotate by 4 pi, then that's trivial. Okay, and yeah. Okay. So that will give you some kind of string. But now, once you get into this game, you can think of many things. I mean, for example, if you have, so each of these corresponds to some symmetry breaking. So this would be U1 to 1 maybe. This one would be O3 to O2, would give you this. So you could have SU3 to Z3. Sorry, maybe I didn't get that right. Okay, let's just ignore this for the time. You could also have SU3 to Z3, in which case you would also get strings, but the strings could have junctions. So you could have one string and then it splits into two strings, a bit like QCD. In QCD, you can have QCD flux tubes that go and split. Basically, if sort of rule of thumb is that that if you have a symmetry breaking G to H, and if you see U1 factors here, and you don't see them here, then you should be alert for strings. Okay, U1 factors in G, so not in H. So this is one sort of red light that you should look out for strings, or if H has discrete factors, which aren't in G, So then you should be alert for strings. Okay, so in this case. In this case, there was U1. Here, there would be a discrete factor in the final group, and here there's a discrete factor over here. So whenever you have this situation, so in particle physics, it's fairly clear that when you have leftover discrete factors, you might have strings, or whenever you have U1 factors that break down, you have strings. Okay, now such strings are also arise in string theory, and we have lots of string theorists here at the IAS. I am not an expert in the area, but let me tell you what those strings look like. So in string theory, there are two kinds of strings. There is the F, this so-called fundamental, and there are the D's, which are the Dirichlet. Okay, and you can also have bound states of these strings. So you can also have bound states. And these bound states are basically labeled by the charge in the F, like how many times there's a winding in the F side and how much there is in the D side. This is F and D. But now you have a very complicated situation. For example, you can have a P0 string come in, a Q0, 0Q come in, and you can have a bound state with a PQ, but then you have many other types going out, right? And now you just imagine the whole space filled with this network of strings. In fact, if I have time, I will show you a network that people simulate. And even if you don't have these junctions, it looks like a mess. But with junctions, it would be, I don't know, no one has done it. Okay. So, and the mass of these strings, the mass per unit length of these strings is given by square root of p squared plus q squared by the string coupling square. GS is the string coupling. So, in fact, this is one hope that maybe we are lucky and string theory is actually giving you a network of cosmic strings. This would be, in fact, probably the easiest way to look for string theory. And I'll say a little bit more a little later about how you might be able to look for these strings in observations. So, okay, let's see. No, maybe I can get rid of this. Sorry, was there a question?
The tension of the superstring is larger than 1.
Sorry?
The tension of the mu is larger than 1 or smaller than 1.
Mu is
Just
the square root of p squared plus q squared by g squared. Okay, from that it looks like, I think there has to be a fundamental scale in there which is missing. So, so that must be the string scale. But okay, I can check on that. Okay, so let me just quickly describe the simplest strings. So if you have, say, U1 strings, then and you study what they look like at formation, there would be some strings. And these strings could occur in two forms. One is an infinite string, and the other is closed loops. Okay, and this by simulating this this process, you find that about 80 to 90% of the strings are in long strings, are in infinite strings that don't close, and in closed loops, the rest is in closed loops. And the number of loops per unit volume of a given length, of a given size, let's call it R, is scale invariant. Which means that, you see there's no other dimensionful parameter coming here. It's just, this is, yes. So this is the number of loops of size R over volume. So it's the number density. Okay, so that's just dr by r to the 4, and the shape of these strings is Brownian, which means that the length goes like r squared by some typical scale. Okay? C is the correlation scale. So this pretty much characterizes the strings at formation. So this is this sets the initial conditions for the evolution of the string.
What's the difference between R and L?
So R is the size. So R would be this, and L would be this. So it's basically a zigzag. If it's going, then you do the end-to-end distance, that's R, and you go along the string, that's L. Okay? And the remarkable thing is that this was the study was first done in the context of cosmology, but then later experiments were done in helium-3, where you also have vortices, which are like strings, and they confirm these exponents, r squared. So they confirm this picture in experiments in superfluid helium-3. Okay. Once you form these strings, what happens? They, of course, start moving, because if you have a closed string, it likes to straighten out. And so there's the action for these strings should be, of course, given by the field theory action. Okay? But the field theory action you can reduce to the so-called Nambu-Goto action, which is just mu integral d2 sigma root the determinant of the metric, the worldsheet metric, and gamma AB is the background metric, the space-time metric, where x, okay. So if the string is described by this vector x, right? So if you have x mu of sigma 0 and sigma 1, right? So this is where this tells you where the location of the string as a time parameter and a parameter along the string. Then you can define a metric, and then you have this action. This is the so-called Nambu-Goto action. It's to get some intuition, let's assume that the string is in a flat background. So g mu nu is eta mu nu. Then the equation of motion can be written as x double dot minus x double prime is 0, x dot x prime is 0, x dot squared plus x prime squared is 1. And also x0 is t. Okay? So these are the string equations in flat spacetime. And the nice thing is they can be solved. And they can be solved in a very intuitive way. And so that's quite pretty. And so let me just describe that. I can use this. So first of all, this is just the wave equation. This tells you that the velocity is perpendicular to the string. The string is along x prime, and you're saying that x dot is perpendicular. So velocity is perpendicular to string. And this actually turns out to be just a choice of coordinates along the string, such that the length measures the energy. Okay, you have a choice. So this is length parameterization. Okay, to solve these equations, it's quite easy. You write x of t and sigma is the sum of left and right movers. Okay? And then, so that automatically solves the first equation. And now you plug that into these two, and what you find is that the next equations imply that A prime is equal to 1 is equal to B prime. So it tells you that A prime and B prime are unit vectors. Okay? These are unit vectors. And furthermore, if you have a closed loop, you have the constraint that A prime is equal to minus B prime. So this is for closure. And of course, in the center of mass frame, these would be 0. Okay, so let's try and draw some of these string trajectories, what you would do is you would take a unit sphere, okay, and now A prime is a unit vector which goes along this unit sphere. So it is some path. Let's say this is A prime, and B prime is some other path. Let's say this is, let me call this minus B prime. It will just be, it doesn't matter, minus, you can flip it. So if you can find any paths on the sphere, any two paths on the sphere whose centroid is at the center of the sphere, that's this condition, then you are describing a loop of cosmic string, including all the dynamics. It's a nice, elegant solution to this problem. But notice that generically, when you draw paths on the sphere, they will go and intersect somewhere. Okay, and this intersection is very important. This is where A prime is equal to minus B prime. But if you calculate the velocity, then that is actually equal to let's call the magnitude of the velocity, then that is A prime minus B prime by 2, and that will turn out to be 1. So it means that if you generically take two paths on the sphere, they intersect, and at that point, the string has velocity 1. Okay? So in other words, you can Taylor expand around this point, and you find that a string goes like this, and then it evolves, and then it becomes like this. And this point is shooting at v equal to 1. Okay, just for an instant. So this is like a whip. You have a string moving around, and all of a sudden, one point gets to the speed of light. Okay, and that point is called a cusp. Okay, so cusps are very generic on if you draw curves like this. But there is one feature of the evolution that is missed by the Nambu-Goto action. Okay, and let me. So the Nambu-Goto action. Remember, you started out with a field theory or a string theory, and you all the string dynamics is supposed to be included in that field theory. From that, you have somehow truncated to the Nambu-Goto action, which is just described as line moving in a certain way, right? What you have missed is that when two lines get close to each other, then what happens? Okay, so Nambu-Goto misses the string interactions. So for that, you need to run field theory. And what you find is that when you have two strings, so let's say this is coming down and this is going up, then this goes into, this is coming down, this is going up, and this is going up, and this is coming down. Okay? So the strings come together and they reconnect. Right? They break each other and they reconnect, and this phenomenon is called intercommuting. And so you might say, well, this it could happen that they pass through, but it might depend on how fast I send them or at what angles I send them and so on. But the answer is that no matter what you do, in field theory, they have always been seen to reconnect. Okay? So the intercommuting probability is 1. Now, I raise this point because in string theory, the same calculations have been done. And there what you find is that this problem in string theory, there you can have PIC, which is much less than 1. Okay? So it means that the network from field theory, that you get a network of strings, will actually start looking very different from the network in string theory strings. And in fact, so this is the reason why some people believe that by looking at the whole network of strings, you might be able to tell whether the strings are coming from string theory or from or some field theory. So, okay. Let me just oops, I can't. Okay. Okay. So, but this intercommuting has an important consequence for observations as well. And that's something you can already see in that picture, is that when these strings reconnect, you get these sharp corners. Okay, these corners are called kinks. Okay, and basically these are corners such that the tangent to the string is discontinuous. Okay? But notice that the tangent, if you differentiate this with respect to sigma, will contain A prime and B prime. And so what you're saying is that these intercommutings actually introduce discontinuities in these paths. Okay? So a string with a discontinuity, with a kink, would look maybe something like this. Right? They would have discontinuities. In fact, if the discontinuity happened here, then basically the kink would destroy the cusp. Okay? Now the reason I'm telling you about kinks and cusps is that you can show that these features on the string are very crucial for their observation. And let me point that out. Let's see. So basically, if you have a string, then the way you can look for it is that it sends something to you. So this could be gravitational waves or photons or particles of different kinds. So you want to calculate the radiation from cosmic strings. So, so what are the couplings? You can have, for example, for gravitational waves, you can work out the energy momentum tensor of the cosmic string, and that will be a source for gravitational waves. So T mu nu for gravitational waves would look like and similarly, you could consider, so this is gravitational waves. You could consider other emission like Goldstone bosons or photons or whatever. I'm not going to write down the couplings, but the point is that the source is a quadratic in the derivatives of the string. Okay, so like x dot, x dot, x prime, x prime. For Goldstone, it would be something like x dot, x prime minus x prime, x dot. So so here's the source, and when you start calculating the power emitted, so like the energy emitted per unit time, this will this will of course be proportional to T mu nu, right? And so you'll get integrals such as so let's see. So you would this would be this would depend on, I'm not going to do the whole calculation, but it would depend on x dot minus x prime, which would be something like, it would lead to basically d sigma plus d sigma minus a prime of sigma minus b prime of sigma plus, and then the Fourier transform, which would be e to the I k dot a, e to the I k dot b. So when you work in the Fourier domain, then you would be Fourier transforming this expression, and you would get an a prime maybe from x dot, a b prime from this x dot, and of course exponentials. Now the point is, so the basic point is here that your energy emitted always depends on these integrals. It depends on integrals I plus minus, which are sigma plus minus, and let me call it a plus minus prime. And now instead of writing a and b, I'm writing a plus a minus, and then e to the I k dot a. So these yes.
Can I just check these dots and primes are worldsheet derivatives?
Yes, so they're with respect to t and sigma, the worldsheet coordinates. Yeah. So the power emitted always depends on such integrals. Okay. Now remember, these cosmic string loops are astrophysical scales, so they're like maybe kiloparsecs, megaparsecs, or even larger. And you are interested in observing things, so like you might want to see how many photons come at wavelengths of say a millimeter or optical, which are completely tiny. So imagine that a huge thing like that, can it emit wavelengths which are so small? And in general, the answer is no. You're looking at very high harmonics. So k here, k is n omega naught, and then the vector k, and omega naught is 2 pi by L, right, where L is the length. But you are interested in frequencies which are very high compared to the fundamental frequency. So that means you are interested in emission at extremely large harmonics, maybe, I don't know, millions of harmonics. Okay? So then such an integral, you only need to evaluate these integrals at large harmonics. And okay, maybe I can just. And then, of course, at large harmonics, I plus minus will be e to the minus some number times the number of harmonics, times the harmonic number. Okay? So in general, this will be the answer, and you will basically get no radiation at very high harmonics. However, there are two exceptions. And the exceptions are, this will go like 1 by n to the 1/3 if there is a saddle point. And 1 by n if there is a discontinuity. Cusp. Actually, it's a little more, people probably hadn't realized it, but there are 3 cases to consider. Okay, so there are these 3, right? So basically what I mean is that the derivative up here would be 0. And mathematically, k dot a prime should be 0. So if your k is aligned in the direction of a prime, right? Remember this is a prime. If your k is pointing in this direction, then you will have a saddle point. Okay? Okay, so but now the power emitted is always a quadratic. It's always I plus I minus. So power emitted is always like I plus I minus. So the exponential is, of course, uninteresting. So you can have 3 cases. One is saddle, saddle. The other is saddle discontinuity. And the third is discontinuity, discontinuity. There are 3 cases where the emission from strings is interesting. Now, the saddle, saddle is that k has to point in the direction of a prime, and it also has to point in the direction of b prime. So that means that a prime and b prime have to intersect. Okay? It's actually minus b prime, but that doesn't matter. Okay. So this saddle, saddle is emission from a cusp. Saddle discontinuity means that this is a kink which is running along a string. A kink is a corner, and basically what happens is that the kink keeps moving along the string. Okay? And a discontinuity is a kink-kink collision. Okay, where two kinks come and collide, and that gives you a discontinuity in both the integrals. Okay. And I won't go into details here, but these three have very different emission features. The cusp is where there's a beam. Okay. So the cusp shoots out a beam in a certain direction, and the opening solid angle here is of order omega L to the minus 2/3. Okay, so in a tiny opening angle, it shoots out a pistol. I mean, okay. The kink emits in a fan-like beam, right? So that's a little harder to draw, but let me try. Right, so it emits in a slice, and this angle here, theta, is like omega L to the minus 1/3. And then a kink-kink collision, I don't know how to draw that because it's happening in time. So kink-kink collision is isotropic. Isotropic meaning that it's in all directions, it's not beamed in any direction. So string radiation is always is the interesting string radiation is in these three forms. Okay? So now, of course, the question, so this is very important for observations because you want to point your telescopes and try and see strings. So one way you would see strings is to watch for these cusps that are hitting, it's throwing particles at you, or these beams, or these other beams. So, so you might ask, well, how many cusps are there? How many kinks are there? And so on. And here, again, there's no analytical way to calculate these things, so people look at simulations. Let's see. Okay, let's just, I think it's simpler to keep these blackboards down and sorry? L is, they could be, so there's a whole spectrum, and I am going to say what the distribution of lengths is. But yes, it could range all the way from horizon size down to very small sizes. And there's a distribution of loops. So, so numerically, what you find is that there are about 0.3 cusps per loop. So maybe, remember, kinks can destroy cusps. So, so there's this question of how many cusps survive in the end. And generally, people will just put a fudge factor number of cusps and take it to be order 1. Now, so these are 0.3 cusps per loop, and you can imagine that you'll have 4 kinks per loop. And this is a tricky business because, which I'll explain, is that kinks can have, you can have a very sharp corner or you can have a very shallow corner. So this 4 kinks per loop you can show by a simple argument. Let's start with a smooth loop and let's have it break into 2. Right? But these 2 are really 2 kinks. Okay, so every intercommutation, every splitting of a loop gives you 4 more kinks. Okay, so yeah, and it gives you 1 more. So let's say you have n loops, and you have 1 intercommutation. Then it goes to n plus 1 loops. But you get, and if you had k kinks here, then you would get k plus 4 kinks here. And by following this argument, you can actually show that the number of kinks per loop, which would be k by n, would tend to 4. Okay. Okay. Now, the interesting thing is that that the number of kinks, as I said, the kinks can be shallow or sharp, and the question is, what is the distribution of these kinks? So you can define what is called the sharpness of a kink. And say psi, and let's say the sharpness in the left mover. And this is defined to be half of 1 minus a prime after the kink dotted into a prime before the kink. Okay? So you can define some sort of sharpness of the kink. And what it turns out is that the distribution of these of the sharpness is peaked at the very shallow kinks. So basically what is happening is that in the history of the universe, at some very early time you form some kink. Okay? And every time you have an intercommutation, let's say the strings formed at 10 to the minus 35 seconds, they have been intersecting ever since, and these kinks have been accumulating all the time. Okay? So even today, those kinks that were produced at a very early time have not been destroyed, have not been smoothed out completely. And that is why you have a lot of shallow kinks. In fact, the number of kinks per unit length is something like 2.4 by t by t star 0.9. So this is work by Copeland and Kibble. And T star here is some early time. It's actually, I did not mention, when strings first form, there's an ambient medium, and that gives a lot of friction on the strings and is very efficient at smoothing out the string. But after a while, the medium becomes less dense, and this process stops, and then the strings are free to move around without friction. And so this is the end of the friction regime. And this is also very early. So you see there's a huge number density of kinks on the string. And so, so there's a good chance that the kinks might actually be more important than the cusps when you go to look for strings. Okay, in the last, I have to describe the string network. And then I want to discuss the observational signatures. So 2 more things. So Matthias was asking about the string network. So, so just imagine this box which has some infinite strings and some loops. So you might be interested in the question, how many infinite strings do I have in my horizon volume? And this turns out to be the number of infinite strings per horizon is well, this is about 100. And these results, there is no analytic derivation. In fact, I should mention that that this evolution of a string network is an unsolved problem, and there is every indication that it's in the same class of problems as turbulence. In fact, there's something called quantum turbulence, which happens at very low temperatures, which is all about how the strings, the vortices in a superfluid, are moving. And so the way that people study this network evolution is basically by running simulations. But if you have some good ideas, then that would be excellent. Maybe use ADS CFT or something. Okay.
Could you say what is the analog of an infinite string in a superfluid? What is the differentiation between
In a superfluid, those would be, in a superfluid, you produce, say, bubbles of, I think, helium-3A. I don't remember exactly all the details, but you have I think, let's see, helium-3P. I think what you do is you start with a container of helium-3b, and you produce a bubble of helium-3a by shooting in neutrons and heating up. And then the thing cools because it's surrounded by helium-3b. And then when it cools, you get, and then they are also rotating the system, so they can extract vortices and count them. But the analog would be things that are going from boundary to boundary. Except that I'm not sure that they are actually, I'm not sure how they would count those. They could count the loops, but it would be hard to count those, yeah.
I'm just curious, when you, in these numerical simulations, how many string lengths can they run for?
How many?
In terms of the correlation length, how many correlation lengths can the simulation run for when you're trying to figure out what happens to the number?
Well, so they are running these in expansion, in an expanding box. So they can, I mean, the old simulations were doing 2 or 3 Hubble expansions, but now they have found, this is a Tufts group that has been doing, they found some new technique and they can run it much longer. So, so it's getting better, but ideally you would need some sort of theoretical input as well. And there has been theoretical input. For example, Polchinski and Rocha, they were calculating the shape. So there are many questions you can ask. What's the shape of a long string? And so you would be calculating correlation functions of the string variables along a long string. And they find various exponents. So that's one thing. You could ask what is the length distribution of loops, for example. But that's a complicated story because it looks like the loops that are produced are big. They're typically horizon size, or maybe 1/10 of a horizon size, and then they split up into lots of little guys. You might ask, what is the shape of a loop? And I think actually that turns out to be an easier answer, and which was kind of surprised me a little bit, even though thinking afterwards it seems fairly clear, that the shape is basically a rectangle. So the idea is that, let me just finish this and I'll get to you in a minute, is that if you have a loop, which is some path, you want to find A prime and B prime on the sphere, such that the dynamics of the loop is such that it never intersects. Now, of course, if you take a very complicated path, then the loop is complicated, and as it's moving around, it's going to hit itself and intersect. So you know that the loops that do not intersect have to be relatively simple. And so the simple loops are like just a little segment here and there. Remember, these are kinks. And so there are 4 segments like this. This loop has 4 kinks, and these kinks here. And basically in space it looks like this, but it cannot be in a plane, because in a plane these would come and hit each other. So instead you misalign it slightly, and so it comes, so when these 2 sides were coming together, they're actually a little displaced and they cross over, and then these sides come and then it keeps oscillating. So the shape of loops seems pretty, it's a pretty nice shape, very simple. Anyway, the length distribution of loops is less certain, but in the literature, what you do is you just adopt the scale invariant distribution. So the number of loops of a given length at a given time is some number which is order 1 times dl over t squared L plus gamma t squared. So this tells you the number density of loops of a given size L at a given time t, and this is in the matter-dominated. And so L, of course, is the length, t is the cosmic time at which you're looking, and gamma is the energy loss rate. Energy loss rate. Okay? So basically what's happening is that loops are shrinking, so their size is changing with time. And so you account for that by this factor. And for gravitational energy loss, this gamma is something like 100 g mu. Mu is the tension, right? Mu is the mass per unit length. So at least once you have this caricature of a model, you can at least work out predictions for what the observational signatures would be. I'm going to, I'll need 5-10 minutes. So now let's, we've already talked about the emission from strings as a possible observational tool. There's also the metric, which is rather peculiar. The metric of a straight string is just ds squared is dt squared minus d rho squared d theta squared minus dz squared. So this is just flat space-time, right? So there's nothing unusual except that 0 is less than theta is less than 2 pi minus 8 pi g mu. Okay? This angle theta doesn't go around from 0 to 2 pi, but it goes from 0 to 2 pi minus something. And what it means is that if you look in the plane perpendicular to the string, then so the string is coming out, then then there's a little wedge that's been cut out. So basically here's the string coming out, theta goes from here to here, and then you have to identify these two edges. Okay? This is called a conical metric, because if you identify those two, then it becomes like a hat, conical hat. And this opening angle is 8 pi g mu. It's sometimes called the deficit angle. Okay? But this metric has some very interesting properties. For example, if you take a source behind, and you are, so here's a string between you and a distant galaxy. So then light can come this way, it can also come this way. Because remember, you have to identify these two. When you identify these two, this light is basically being bent this way. So which means that you will see two images. So this tells you that there will be lensing, and the opening angle will be approximately delta. There will be some geometric factors also, but roughly 8 pi g mu, you'll see two images. The other interesting thing is that let's say this had some shape to it. Let's say it was like this, like an arrow, then this would also be in the same direction. That means that the parity of the image is not changed. Okay? And this is an important observational tool. The other thing is that if this is an extended guy, right, then this part will be lensed. How does that go? This part will be lensed, but this part will not be. It is too far away. Like this, there's no bending here. Okay? Like this part, this ray that goes here will actually go down here. So that part will not be bent, but this part will be bent. Furthermore, the edge that is bent is going to be a sharp edge. So if you see lensing and you want to know whether it's by a string or by some other object in between, then one feature that you expect to see is a sharp edge. Okay? And I'll show you a picture if I get to it. The other thing is that let's say the string was moving with a certain velocity v. Then of course this distance is not changing because this is just flat, but this distance is changing because now after time dt, this has to go through a shorter path. Okay, do you see that? So which means that this image is as if it is approaching the observer. So this image will be blue compared to this image. This would be red. Okay? So what you expect to see is a slight difference in the temperature of the two images. One is Doppler shifted with respect to the other. Now, in the case of this is a small effect. It's again order delta. But in the CMB, if you had the CMB and you had a string and you were here, what you would expect to see is that the CMB on this side would be red and on this side would be blue. So you would see a line on which one side is red and on the other side it's blue, and there's a sharp discontinuity in between. So that's another way people look for strings, is by discontinuities in the CMB. Okay? This is called the Kaiser-Stebbins Gott effect, where you get these temperature discontinuities. Okay. I only have time to basically list the observational constraints. So let me just do that. It's too bad I can't list this one. Okay, so observational constraints. The first is step-like discontinuities. In CMB. And these give you that G mu should be less than about, so again, now the signatures depend on the model that you assume for the strings. So two different groups give you two different constraints. One gives you few times 10 to the minus 6 and few times 10 to the minus 8. Just to give you a ballpark figure, G mu is roughly the scale at which the strings were formed divided by the Planck scale squared. So if you have G mu of 10 to the minus 6, then that is telling you eta of 10 to the 16 GeV, which is, I think, an epoch of 10 to the minus 35 seconds after the Big Bang. So you're constraining that strings formed after 10 to the minus 35 seconds after the Big Bang. Then of course, these strings are energy momentum that is stirring up the fluid at recombination. So you have constraints from CMB anisotropies. And because as Matthias mentioned, well, that you get these beautiful acoustic oscillations, CL, TT, L, and they depend on there being a coherent oscillation. The phase has to be the same for all the modes. But for strings, that's not the case, and they are acting at random, so they would give you some effect like this. Now, if there are too many strings, or they're too heavy, then they will ruin these acoustic oscillations. And that gives you a constraint on the string parameters, and this is G mu of 6 times 10 to the minus 7, less than 10. But the strongest constraint is claimed from the millisecond pulsar experiments, which are this is millisecond pulsar. And if you haven't done it, you should go to the web and search for millisecond pulsars, and you will get an audio file, and you can actually listen to the pulsar. It's very fascinating that you can actually hear the pulsar signal. Anyway, the idea is that the pulsar is here sending a signal to us on Earth, but then there are gravitational waves that come and hit the pulsar, and they also hit the Earth. And these gravitational waves, they sort of shake the Earth and shake the pulsar a little bit, and they give you noise in the timing of the pulsar. And that constrains, so that constrains the gravitational waves. The stochastic background of gravitational waves is constrained by these pulsars. But strings produce a lot of gravitational waves because there are these heavy objects which are flying around at relativistic speeds. So that constrains the string tension. And here, most of the gravitational waves are produced by cosmic string loops. So it depends on the model of the loop, but you have constraints of less than 10 to the minus 9. And this is for intercommuting probability of 1, but for intercommuting probability of 10 to the minus 2, 10 to the minus 2 is it? Sorry, I can't read my own handwriting. 10 to the minus 3. So such as might happen for string theory strings, you get a much more stringent bound on G mu. There's also lensing, but so let me just quickly, can I have the slide, the computer, please? Let me just show you just for 2 minutes. Okay, and this will be the last bit. So here is, okay, so the resolution is messed up, but when you do strings at formation, they look something like this, right? And you can see some loops. There are those circular guys, and then there are the infinite strings. So it's a whole tangle. Let's see. I should play this slide. Play. That's better. Yeah. Okay. And then after they hit each other and they evolve and they break up into loops, the network starts looking something like this. And you see these long strings that are crossing the box, and then you have these little tiny dots which are all loops. Then that's the string box, and here is a simulation. Let me just go back. How do I? This might interest you. Here's a little movie of a big string loop breaking up into little loops. And you can, if you pay attention, you can see that the loops that are coming off are kind of squarish, rectangular. The red is wherever an intercommuting happens. So let me just stop this because I know Matthias must be getting impatient. But anyway, you can. And finally, I wanted to show you an image of what a string lensing would look like on the left, and you can see the sharp edge. And actually, this image, actually the precursor to this image was people thought that it might be due to a string, but then the Hubble Space Telescope looked more closely and did not find any edge in that image, and so they said it cannot be a string. Okay, so that would be the expected image, and this was the close-up look by the Hubble Space Telescope. So there are many false alarms in the lensing when you look for lensing, and this was one of them. Okay, thank you.